Substitution nucleophilic first order SN1 reactions prefer to have the solvent be a polar protic solvent. This is in direct contrast to the SN2 reaction where the solvent must be polar but aprotic. Here what we're trying to do is we're actually trying to stabilize a charged intermediate. So in our substrates, and let's imagine a tertiary chloride, what we absolutely must do in order for a reaction to take place is have the chloride leave. Said another way, we will actually form two ions. We will specifically form a tert-butyl cation in this case, but we will also form a Cl-. And the solvents that can best stabilize both of these at the same time are polar protic solvents, because in order to stabilize an anion like this, the best way to do it is to have, say, a hydrogen of, say, methanol floating around nearby where you have a substantial amount of delta plus that's interacting nicely with the Cl-. So what you want is for this chloride to be absolutely surrounded by hydrogens that can engage in some sort of hydrogen bonding or other good dipole-dipole interactions. Your polar protic solvents have these protons available that have a significant amount of delta plus on them. This is what lowers the energy of the anion. Obviously, the oxygens on, say, methanol can donate electron density into this orbital right here, and that's precisely what causes them to potentially bind to the system. Once again, what you're trying to do in a reaction coordinate diagram sense is to lower the energy of this intermediate. The hard part in one of these reactions is getting the chloride to leave. You want the chloride to leave, and you want the cation and the anion to get far enough apart from each other that they don't immediately recombine, which means that the solvent really has to do a nice job of solvating both the Cl- and the cation, both. And the best solvents to do that are always going to be ones that can interact well with both members of the species, with both the minus and the plus. So your polar protic species are the ones that can actually separate the ion pair and then react further. Said another way, what they can do is stabilize both halves, the plus and the minus, of the system that results. This is by contrast to the SN2 reaction, where you're not actually trying to separate ions from each other. All you're trying to do is to minimize the energy of a transition state. The moral of the story, a polar protic solvent tends to lead you towards separation of charge, solvation of the anion and cation, whereas a polar aprotic solvent tends to encourage these to stay bound to each other.